Welcome back to our series on the history of mathematics. We are continuing our work through Chapter 2 of Stuart Hollingdale's book, Makers of Mathematics. Our focus is on the Pythagoreans. This is a proof that's actually discussed in a fair amount of detail in the book, but I would like to go ahead and give even more information. So this is a proof that every student of mathematics should be familiar with and should be able to reproduce. So the claim that we're trying to prove is that there is no rational number x, so that x squared equals 2. Now this proof is going to make use of something called a lemma. A lemma is like a little theorem. Typically, a lemma is a statement that you prove, but the reason that you prove it is so that you can use it as a stepping stone to help you prove something else. So in general, a theorem is of interest in its own right. A lemma is of interest because it is useful to prove theorems. So our lemma is that if p squared is even, that is logically equivalent to p being even. So let's go through the proof of this lemma. This is something that is especially nice to prove by looking at different cases. So the claim involves p squared being even. We're actually going to look at the value of p. So case 1, p is even. Well, if p is even, that means it is a multiple of 2. So if p is even, then it must be equal to 2 times some other integer. We square both sides because we're interested in saying something about p squared. If we square 2k, we get 4k squared. You have to do 2k times 2k. You can collect the 2's and you can collect the k's. And of course, that is equal to the expression I've got right here, 2 times 2k squared. And this shows us that if p is even, then p squared is even. I'm sure you're familiar with this notation. It's used for an implication. So if this is true, then this is true. The other case to look at is when p is odd. Now, if p is odd, that means it exceeds a multiple of 2 by 1. So every odd whole number can be written in this form for some value of k. For example, if I wanted to write the number 7 in this form, it would be 2 times 3 plus 1. Since we're saying something about p squared, we look at p squared. Well, if p is equal to 2k plus 1, then p squared must be equal to 2k plus 1 squared. We multiply out and combine like terms and we get this. Notice that these two guys are both even, so we can factor out a 2. Naturally, the 1 is just stuck there. So if p squared is not even, so if p is not even, then p squared is not even. Okay, so that establishes our lemma right here. The only way to get an even value for p squared is to start with p being an even number. So now that we've got our lemma, we can proceed to the proof of our claim. Let me get a clean slate here. So once again, we're working on this claim. So there is no rational number x so that x squared equals 2. And our proof of this claim is we're going to work to set up what's called a contradiction. So this is an indirect method of proof, and it was used quite a bit by the classical Greeks. So we're actually going to assume that our claim is false, and then we're going to see what happens. What are the logical consequences of this being false? Okay, so suppose there is a rational x with x squared equal to 2. So if x is rational, that is equivalent to saying that x equals p over q, where p and q are whole numbers, and furthermore, we can assume that the GCD of p and q is equal to 1. So in other words, we can choose these values of p and q to have no common factor. If there was, we could just cancel it out. For example, nobody would write 2 over 10. We would cancel the factor of 2 that is common to the top and the bottom and write 1 over 5. So every rational number can be expressed using a numerator and denominator that do not have a common factor. So if this is true, then we're really saying this. So x squared equals 2 is logically equivalent to saying that p over q squared equals 2. Now, if we do the algebra over here, you're squaring a fraction. So you take p over q times p over q. Of course, you would multiply fractions straight across. So the left-hand side is p squared over q squared. And you can multiply both sides of that by q squared to get this. So p squared equals 2q. And by the lemma that we just proved, by the lemma, that means p is even. So we can take p equal to 2 times some other integer. Now let me scoot that up a little bit here. Since p squared equals 2q squared, we see that this is saying 2k squared equals 2q squared. Now, of course, we're squaring a product here that's equivalent to squaring each factor. And that means I've got 4k squared equals 2q squared, or 2k squared equals q squared. Scooch up a little bit more there. So q squared is also even. By the lemma, this means q is even. So since p and q are both even, we've got two numbers that are divisible by 2. Therefore, the GCD of p and Q has to be at least 2. Now this is a contradiction. Up here you can see that we can take the GCD of P and Q to be equal to 1. So the GCD of P and Q is equal to 1, and the GCD of P and Q is also equal to 2, or actually it's greater than or equal to 2. So you can't have both of those two things being true at the same time. So that must mean that our premise was faulty. So let's go back up to our premise here. The premise was that there existed a rational number x with x squared equal to 2. So that premise leads to a contradiction. So that means our premise can't be true. Since we arrive at this logical impossibility, that must mean our starting point is flawed. So this proof by contradiction is a technique that students of mathematics should be familiar with. So any math student should be able to reproduce a proof like this and understand the technique of proof by contradiction.